Hello everyone, welcome to the P1 program. This lecture is called P107.3, right? In this lecture, we are going to look at the uniform circular motion, and we will look at the geometrical interpretation of uniform circular motion. So, it's a geometrical interpretation of uniform circular motion. So what we have done is a mathematical interpretation. That's what we have looked at, right? We have done the hard way, finding out the different aspects of rotational motion, like acceleration, the radial direction, in the tangent direction or theta direction. We have found out the acceleration vectors, and we have already found out the velocity vectors, and we have introduced omega and alpha, right? Omega and alpha vectors, which are angular velocity and angular acceleration. So I'm going to look at this in a simpler way, in a geometrical way, like imagining things and doing it, right, without much mathematics. So this is the basic format that most of the universities follows. So basically most of these educational institutions follow this kind of a method, which is easier to do. So for that, let's assume that you have a circular body which is rotating around, right? And it has a velocity. So at some point you can see that the velocity vector at each point, at one first point, which is r of t, and the second point you can call it r of some t plus delta t, right? So in r of t and r of t plus delta t, 2 points, two vectors, two positional vectors, and this is what the velocity drives. Like velocity drives as a tangent this body from this point to this point, right? It drives from that there to there. So what we can do now is that we can consider this as a vector, right? So you can consider this as a vector with theta angle inside. You can consider velocity vectors, right? Velocity vectors. And now these two velocity vectors, and you can draw a triangle. Okay, maybe I'll draw it here, draw it neatly here, anyways, somewhat neatly, relatively. Anyways, so this is the velocity vector, the positional vectors giving you the velocity vector. So this is v of t at time t, and this is v of t plus delta t, right? So that's what happens to the velocity after some time, and there is an angle theta in between. So this can be subdivided into two compartments, each right angled triangles. This will have theta by 2 angle, and this will also have theta by 2, right? Now what I can do, that what I'm intending to find out is that geometrically identifying what the velocity and acceleration is. So in order to do that, I can write down sine theta, right? Sine theta by 2 to be exact. So it's sine theta by 2 will be equal to the opposite side, which is the magnitude of these vectors, right? So which will be v of t. I'm taking one of the two sides, so it's v of t divided by, right? So that's the opposite side, so that's the hypotenuse, anyways. So I'm sorry about that. So it's the hypotenuse, so actually it is going to be the opposite side. So this is theta by 2, so the opposite side will be, this will be the vector v, right? So this will be the vector v, uh, which can be found out by subtracting v of t and v of t plus delta t. So if you look at this in a simple manner, you can see that if v is like this and v at t plus delta t is like that, then two vectors, the difference between two vectors will be this resultant vector, right? So the difference between these two will be the resultant. So the resultant vector will be the delta v, right? The actual velocity, right? So that's the velocity vector here, right? So using the triangular law or parallelogram law, depending upon your choice. So this distance will be delta v, right? So this distance will be delta v, not v, delta v. Anyways, so opposite side will be, so if you take this triangle, and I'm going to redraw it here, and this is theta by 2, and this is v of t, and this is v, magnitude of v by 2, or delta v by 2, right? So delta v by 2. So you can say sine theta is equal to delta v by 2 delta v by 2. I don't know what's wrong with me. Okay, so it's delta v by 2 divided by the hypotenuse, which is v of t, right? So that will be that. So you can say sine theta by 2 will be approximately equal to theta by 2. So that will be equal to, using the last lecture, the small angle approximation which we have derived, you can use that, and you can say that delta theta by 2 will be delta v by 2 v, which is a vector, okay, magnitude of that vector v of t. So you can say, now you can, what you can say is that you can say delta v must be equal to some theta, 2 and 2 will cancel, and some theta times magnitude of vector v, right? I'm going to call this equation 1, right? So that's the velocity vector, right? That's the velocity in that part. That's the velocity difference in velocity. Now if you look at the acceleration, right? So if you look at the acceleration, I don't want to zoom out much, so it's acceleration. So if you look at acceleration, you can see that acceleration, vector acceleration, will be some limit delta t tends to 0, delta v by delta t, right? So that will be the textbook definition of acceleration. So you can write it as dv by dt, which is differential of v with respect to time. So the acceleration, if you can substitute that delta v back into this equation from here, that's the velocity change. So you can say acceleration is equal to limit delta t tends to 0. It's too small, okay, it's theta times, so delta t tends to 0, v times delta theta by delta t, right? So you can substitute that. Now I can take the magnitude of velocity outside, and you get velocity times, which is magnitude, times limit delta t tends to 0, delta theta by delta t. So that's the textbook definition of a differential, which is called v, which is a vector, velocity vector. This is not, this was the vector, right? This was not the magnitude. So velocity vector times d theta by dt, right? So that's v times d theta by dt, which is equal to acceleration vector. So now you can say acceleration vector is equal to velocity vector times omega, right? So that's also a vector. So that's acceleration vector derived out of geometrical interpretation, right? Now understanding this vector, the direction of this vector, now let's look at the direction of this vector. So for that, what we can do is that we can use the, always has to use the right-handed coordinate system. So if you have something rotating in this direction, and it is shifting from some angle theta, then you can say that d theta by dt, which is the time rate of change of theta, right? So that's time rate of change of theta, also called omega. So if you look at the right-handed coordinate system, you can see that if you have an axis x here and y axis in here, then you can see if you go from here to here, then using the right-handed thumb rule, right? If your fingers are crossing like this, I have explained this before, and then the thumb will point you in the direction of, fingers are crossing like this, then the thumb will give you the direction of what, the cross product, so you of the resultant vector. So it will be perpendicular to this whole plane, so it will be in this direction, so it will be in the axis c axis, right? So this, the resultant will be in the c axis. So the, if the change is in this direction, then the resultant vector d theta by dt, which is omega, will be in the axis of the, you can call it c cap, right? So it will be in the c cap direction. So that's in the right-handed coordinate system. If you are using a different coordinate system, then everything else will change, including the cross products. The values of all those will change subsequently. So you have to, you can use your, feel free to use any coordinate system that you want, but if you do that, then you have to redetermine every aspect of cross product, dot product, the resultant vectors. Every aspect has to be changed subsequently, right? So always use a right-handed coordinate system, which is the recommended way of doing problems. Now you can write down that omega will be equal to d theta by dt in the z cap direction, right? So you can write down that it is some magnitude of omega of c in the z cap direction, if you want. So you can say that, which is the omega c will be the magnitude of d theta by dt, right? So that will be omega c. So that's about omega. Now if you want to visualize that, if you want to have a visual representation of that, if you are rotating like this, right, in this plane, then you can clearly say that omega will be, using the right-handed thumb rule, it will be in the up direction. So omega of c will be in the direction up above. And if you are rotating opposite, right, in this direction, the omega will be facing down, it will go down. So omega will be in the minus c cap direction, and this will be in the plus c cap direction if you choose it such, in a such a way, right? So you can now say that v, velocity vector, which we have defined, which we have found out, which is omega crossed into r, right? So that is velocity vector. So that will be some d theta by dt in the z cap direction or minus z cap direction, depending upon the point which you chose, times the magnitude of r times r cap, right? So that will be that. So it will be d theta r times d theta by dt times z cap crossed into r cap, right? So it will be z cap crossed into r cap. So what is z cap crossed into r cap, right? If you look at this rotational motion, you can see that z cap, if this is z cap, right? So this is z cap, this is the direction of omega, and this is the radial direction, which is outside from the center, which is r cap, right? So now you can clearly see that omega will be the velocity vector will be in the direction of z cap crossed into r cap, right? So it's z cap crossed into r cap. So it's z cap crossed into r cap will be, you can use the right-handed rule. So you have to start from z cap and then move to r cap. Your fingers has to direct in that direction. So in the right hand, you can see that if this is the plane that you're taking, right? So this is the plane that you're taking, then the perpendicular in the right-handed coordinate system will be into the blackboard, right? Not outside, but into the blackboard. So it will be in the direction inside this plane. So inside this plane, right? So that will be the direction of velocity, right? So velocity will be in that direction. So what is that direction? So if you have a circle like this or a circular path like this, then this is the radial direction, this is the c cap direction. Then what is this direction? This direction, okay, what will be that direction? That direction will be the change in theta direction. So it will be the theta cap direction. So velocity vector is in the theta cap direction. So you can say that velocity vector is equal to r times, right? Velocity vector is equal to r times magnitude of r times omega times theta cap direction, the theta cap direction. So that's velocity vector, which we have already found out in a different manner. Now it's a geometrically comprehensible manner. Now let's do a simple problem, and I have to cover almost all of these things, that's why I'm doing this. Anyway, one method was enough, but let's do this in the second method as well, just to understand the depth of this thing, right? It works in both ways, it's the same result in both ways, which is fun to watch. Always it is fun to watch, right? So now let's do a problem. So it's a problem. So this problem, let's say there is a rotatory path with the radius r, and some r is equal to some 2 meter. and theta, which is a function of time, right, which will be 3t minus t cube, right? So let it be like that. Let's find out what the velocity is just to understand the theory, right? Velocity and omega. Let's find out when will omega is equal to 0. So is there a point where angular velocity is equal to 0? Let's find out that. So what you have to do is, now omega is just straightforward. You can say omega will be equal to what? Omega will be equal to some d theta by dt. So that will be equal to, you have to take the derivative of d theta with respect to t, right? And then you get some 3 minus 3t square, right? 3 minus 3t square will be the answer in the k cap direction, right? In the k cap direction. So that will be the omega. So you found out omega. Now what is v of t? Well, v of t is just r omega, right? So it's r omega in the theta cap direction, the magnitude of them in the theta cap direction. So that will be, r is just 2 meters, so it's 2 times 3 minus 3 t square, right, in the theta cap direction. So that is just equal to, this is just basic problem anyways, it's easy to do, t square in the theta cap direction, right? So that's velocity vector. Now let's find out at what point does omega will be equal to 0. When will the angular velocity is equal to 0? So all you have to do is just substitute 0 to omega and you get 3 minus 3t square is equal to 0. So that means you can say, what you can say is that t square will be equal to 3 and 3 cancel, so it's 1. So t is equal to 1 second. So at 1 second the omega will be equal to 0, right? Angular velocity will be equal to 0. So that's how you can use these equations and to find out complicated paths, right? Complicated circular motion when there is no uniform velocity, or there is a changing velocity when the particle is rotating around a body, right? So you can use it like just there. Now what I'm going to introduce is that I'm going to introduce some pure basic concepts, right? Some concepts that we have to remember, which you have seen earlier as well. So the first concept is that we have gone through, which is a of r, which is the radial acceleration, which was equal to some minus r times omega square r cap, right? So that was radial acceleration. And we have also found out the tangential acceleration, which is angular acceleration, which is r alpha times in the theta cap direction. So that was what we have found out from the first lecture. And now we have also found out that velocity was equal to r times d theta by dt, uh, d theta by dt in the theta cap direction. Even now, which is r omega in the theta cap direction, we have found that out as well. Now what we can do is that we can substitute that in the equation of acceleration. So acceleration equation will looks like r omega square, which is the radial acceleration, which will be equal to some v omega, because v is equal to r omega, right? So v is equal to r omega, substitute that back in, so you get v omega, right? So now what we can do is that we can if you rotate around a body, right, if you go around a body, then the total distance or circumference, which will be equal to, the circumference will be equal to s will be equal to some 2 pi r, right? So that's the circumference, which will be equal to some velocity times time, right? Speed is equal to distance is equal to speed into time, or velocity into time, that's displacement. Now you can say time will be equal to 2 pi r by uh, v, right? So 2 pi r by v. Now what we can do is that we can substitute v back into this equation. So v is just 2 pi r by what r omega. V was r omega. Now you can say that t is equal to 2 pi by omega, because r and r will cancel. So t is equal to 2 pi by omega. Now there is something called, this is called the time period of oscillation. So it's the time period of oscillation, right? So that's the time period of oscillation, which is 2 pi by omega. So that's the time period of oscillation. And let's this is for one oscillation, what how much time will it take. That's what it says. If omega is some value, then you can find it out using that straightforward equation. You have been seeing it for a long time, so I'm not going to spend much time on that. Now there is something called the frequency, right? Frequency is equal to 1 by t, right? Why is it 1 by t? So if you have, frequency is the number of times that you circulate in 1 second, you go around in 1 second, right? So how many times would you go around in 1 second? So if it's 1 second, if you can say, if it's one cycle in half a second, right? If it's one cycle in half second, or say 2 seconds, 2 seconds it's one cycle, then what will be the frequency? So you can say in 1 second it will be uh, half cycle, right? Half cycle, because it was one cycle in 2 seconds, so in 1 second it will be half cycle. What did you do was, you just found out the time by dividing, right? Time by dividing, in the time by dividing the factor 1 by 2, right? So you found out that time, right? In 1 second it's going to be half a cycle. So that's how you can find out the frequency. So you just, what you did was, you just divided the time, the number of time divided by the number of cycles, or you can call that cycle frequency, right? From the first case. Or you can do in 1 second you just multiplied it, divided it by 1 by 1 by 2, so you get 2 seconds, 2 cycles. So that's what you do. So you can always find out the number of cycles by dividing the total seconds, or the fraction of cycle you have completed in the number of times, right? So there is a generic equation for frequency, which is 1 by t. So now you can use that for your advantage. So now you can say here, t is equal to 2 pi by omega. So omega is equal to uh, omega is equal to 2 pi by t, right? So 1 by t is equal to frequency, you can call it f if you want. So it's 2 pi times f, right? So that's omega. So you have a new quantity which is called 2 pi f, which is omega. And if you are given a frequency like 100 times in 1 second, 100 times you go around in 1 second, you can use that. You can have to multiply it with 2 pi, and you get the omega, right? If you get the omega, you can use it to find out, if you know the radius, you can find out the velocity, right? So velocity is equal to r omega. So you can use that kind of information. That's the advantage of having this in place. And now acceleration will be is equal to some v omega, which we have discussed. So it will be r omega square if you want. So it is actually radial acceleration, which is r omega square. So omega, you can substitute that back into this equation. So omega was just what omega was just 2 pi by t, or 2 pi f. So it will be r times 2 pi, which is 4 pi square r f square, right? R f square, or which will be equal to so if you, in terms of time period, it will be 4 pi square r by t square, right? Or we can find out the velocity in terms of omega, frequency and time. You can substitute that, it will be r times 2 pi f, or which will be equal to 2 pi r by t, right? So that's how you can use that information, frequency and the what time period, right? So the time period is the time required for one complete circulation, and frequency is the number of circulation that you have in 1 second. So that's I'm going to stop it here. Next time we are going to look at the Coriolis force, and maybe do some problem as well. Okay, so I hope you guys benefited from this, all this, and let's see you next time.